Stark effect. So the Stark effect is nothing but if you are placing your light source in an external electric field of at least some 100 kilovolt per centimeter of strength, then all those levels, all those lines which are coming out of that source will split into different components. Okay. In this case, this is because of external electric field instead of magnetic field. Whatever we discussed so far is because of the effect of magnetic field. Zeeman effect is due to the effect of weak magnetic field. Fast-Back effect is due to the effect of strong magnetic field. Here we will discuss about the effect of external electric field instead of magnetic. So as the source of light is placed strong electric field and that strength of that electric field is at least some 100 K per centimeter. So this is the strength of that electric field. So in this case, every line in every line of Balmer series. So this was first observed in this particular series of hydrogen. So in Balmer series, every line of that Balmer series splits into different components. So unlike Zeeman effect and Fast-Back effect, we have electric field here, and this is strong electric field. And similar to this Zeeman effect, we have pi components as well as sigma components also in this case. So if you consider that pi components means they are parallelly polarized components. And sigma components are perpendicularly polarized. So, so this effect is nothing but splitting of spectral lines of atom or ion or molecule in presence of electric field. Okay, so if you want to define this particular effect, this is nothing but splitting of spectral lines of atom or ions or molecule in presence of external electric field. So we already discussed about these components. So these 5 components which are parallelly polarized, which means that the electric vector parallelly means this electric vector is parallel to the applied electric field in this particular case. Similarly, here the electric vector is perpendicular to the applied electric field. Means that if you are applying electric field in a particular direction, and we are getting that pi components and sigma components, like the lines which are coming out of that source, consider both of their direction, then that electric field, the electric vector which is coming out because of that Stark effect, will be parallel to the external electric field direction. Similarly, if it is perpendicular, then it is called as sigma component. You will be applying, for example, electric field in this direction, electric field, and your sample is there in this electric field. Your source is here. So you are applying this electric field in this direction, like this. So if the field, the light which is coming out of this material after Stark effect, which is also coming, which can also will be in this direction, can be in this, which means that its electric field direction can be in this direction or it can be in this direction. So depends on this, its polarization will be different. So if that electric vector which is parallel to this external electric field, then it is called as the pi components. And if it is perpendicular to the external electric field, then it is sigma components. Or the pi components will be having polarization in such a way that which are parallel to the electric field, parallelly polarized. But in the case of sigma components, these are perpendicularly polarized. And in this case, for the case of Stark effect, the selection rules for selection rules for transition delta mj equal to, there is also some dependence on L values. I will discuss these selection rules later, but as a point, I will just put it here, 0 plus or minus 1. So this 0 will be your pi component, and this 2 will be your sigma component that we already discussed in the also. So this 2 will give you that sigma component, this 0 will give you pi component. So if the shifted lines appear in absorption, then the effect is called as inverse Stark effect. Instead of let's suppose this is your spectral line which is coming out. I will just show here what that means. Suppose these are the lines which are coming out after this application of this electric field. You are getting 2 lines like this, which are green in color, which means that they are having some approximately that kind of wavelength. Okay. So in this case, you are getting 2 lines here. Okay. Distinct lines you are getting. But in some cases, you will be getting white color. I will just show here. Just show that. Suppose your screen is like this. So in some cases, so this is your wall, and you will be getting your spectra like this, green color like this. I will just put it as white wall. Okay, so this is your screen that will show you that spectral lines. So this will be showing green colored spectra like this. Okay, in that white wall. And in some cases, you will get dark color. In this particular case, we will be having dark color like this. And all other phases, you will be having the spectral lines. This white means that the complete spectra is coming. In some cases, it will become dark. In some places. So that means the particular wavelength is absorbed in that particular case. So we are not actually getting that spectra out from that particular sample, but we can see that there is some spectra which is missing. Some lines are missing. And in that case, you can say that as the inverse Stark effect. So if the shifted lines appear in absorption instead of emission, we are getting absorption lines like dark bands. We cannot have any kind of radiation, but we can see there is some lines which are missing. Okay, which means that they are absent. They are absent and be observed from these dark bands. Okay, so that is the lines appear in absorption. The effect is called inverse Stark effect. So these are some points related to this Stark effect. Consider. Now, if you consider the hydrogen line, its main features or important features of Stark effect. The first one is that the all hydrogen lines, in this case, first point, that is all hydrogen lines form symmetrical pattern, but the pattern depends on the quantum number n. So, all hydrogen lines shows symmetrical pattern. Okay. But the pattern depends on quantum number n. We will discuss about that later. So if you have if you are considering that Balmer series or any of these of those hydrogen series, in those hydrogen series, if you put this electric field, external electric field, that hydrogen source, if you put in an external electric field, that line will split. Hydrogen lines will split symmetrically with respect to that central line, and but that splitting or the pattern, how much it splits, that depends on your uh, principal quantum number n. Okay. And second point is that the wave number shift are integral multiples of the field, which is proportional to the strength of electric field and is same as of the hydrogen lines. Just write it down here. So the wave number shift is uh, in proportional to the strength of external electric field is applied and which is same for all hydrogen series or hydrogen lines. So if you consider that wave number shift from the fundamental line, that will be proportional to the external electric field which we apply. And if you consider any of those hydrogen lines, this shift will be equal. This shift, if you consider, that will be same. We will discuss that later, all these points individually later. And the hydrogen lines involving lower energy this is taking much more time, more n. Lower energy state means small principal quantum number n, such as H alpha, H beta lines, etc. They show only symmetrical splitting proportional to the electric field about their phase line position. These kind of lines with lower energy state or lower energy, lower principal quantum number, they show the shift which is proportional to the applied electric field. Okay. So only symmetrical splitting, in case of energy level, it is splitting, which is proportional to the external electric field. And this particular effect, which is called as linear Stark effect. Linear Stark effect. When the splitting of energy level is proportional to the electric field strength. And for lines involving higher n values, or energy level you can consider. So for lines involving higher states, higher states means high n value, high municipal quantum number, okay, such as H gamma. This two we have to consider here. And H gamma and H delta, higher order of these spectral lines, the lines which are involved with a high n value, such as H gamma, H delta. The Stark effect shows unidirectional displacement proportional to the square of electric field. And this particular effect, this is known as or quadratic. This one is linear, this is quadratic. Stark effect. So here it is linear, or you can call this as first order Stark effect, and this is the second order Stark effect. So in this case, you are splitting, or that uh, displacement of spectral lines, which will be proportional to the electric field strength. Okay, but here it will be proportional to the square of electric field. That is the difference. Here we have the energy level splitting. If you consider delta E, this will be proportional to the electric field which you apply. Okay, and here we have delta T. This is also proportional to delta T. Because the same delta T, which is proportional to delta E, will be proportional to applied electric field. But here, this delta T will be proportional to the applied field square. Okay, when you consider the higher order states or higher states with the high n values. So in this particular case, if you consider H gamma, H delta like lines, we'll be having, which will be coming from higher order. We consider N1. So what that means, I hope you know that Varma series. So N1 will be here. All other levels N2, N3, N4 are coming here. So if this N2 is from this N2 level, which is coming to this N1 level, we'll be having that first spectral line. Okay. Similarly, if you go for any higher levels, we'll get the other series, N3, N4. Sorry, if it is coming from here, then we have different. So this is like this is your H alpha, beta, like just confirm that what is that N1 and N2 values. But it will be like this. But when you are considering these small values like this, N1 and 2, like order of that, then you will be having this delta T, which is proportional to this electric field. That is, that means that your spectral shifting, that is delta T, which means that your spectra will be like this. Spectral line, for example, you are having two spectral line like this. Then delta T is that shift between these spectral lines. So this spectral line shift will be proportional to the applied electric field. If you increase that electric field, this shift will increase. If you reduce that electric shift will reduce. But in this case, if you are considering this higher order transition from N5, N4, it is coming to this state, then in such cases, we will be having shift which is in the order of E square, which will be proportional to E square instead of E. So if you are increasing your electric field, it will be shifting very quickly, much more with much more higher value, or variation will be larger in this particular case because it is shifting, its shift is proportional to E square. So a small change in E will produce shift in very large shift because we are having shift is proportional to E square in this case. So if your order is very high and value is high, then your shift will be larger and which will be proportional to E square. And such kind of Stark effect is called as quadratic Stark effect or second order Stark effect. Yeah, but if it is proportional to electric field, the shift is proportional to electric field strength, then it is linear Stark effect. We have only power which is equal to 1 here, so that is linear. So this is linear Stark effect or first order Stark effect. And in the case of the first order Stark effect, which is restricted to the hydrogen-like atom, and occur only in fields which is large enough for the fine structure to become negligible. In other atoms shows second order, which is generally very small. So this I'm not going to write all those things. So I will just put it here. So if you consider that first order Stark effect, we told that the shift will be proportional to E, external electric field. Okay. So this is possible in hydrogen-like atom. And occur only in when the field is large enough. This will occur when that electric field is this particular first order Stark effect occur when the electric field is large enough. The electric field is large enough. It is large enough for the fine structure to become negligible. Large enough for the fine structure to become negligible. And in the case of other atoms, heavier atoms, unlike hydrogen, they show the second order Stark effect, but it is considerably very small. Okay? So first order Stark effect you can observe in hydrogen-like atom with a very small size, and the order of these quantum numbers were very small. In such atoms, you can observe this first order Stark effect. So if you are considering any heavier atoms, which are larger in size, and we have different n quantum numbers, and then in such cases, the second order Stark effect can be observed, but still it is very small. So in this first order Stark effect, this electric field is has to be large enough in such a way that the fine structure can be neglected. What that means, in fine structure, we are having LS coupling. Okay, we are having LS coupling, but we are not considering this LS coupling when you are considering this Stark effect. Okay, because this Stark effect will be dominant. Electric field which we applied will be larger enough in such a way that we can neglect this fine structure or LS coupling. Okay, so the electric field should be large enough for the fine structure to become negligible. In such cases, we can observe this first order Stark. So which means that the shift will be very large. The shift will be very large in this particular case. As you compare with this LS coupling and G-man effect, when you consider that when you apply large electric field, you can neglect this LS coupling which is happening inside the because of that angular momentum part. So we are not considering that part because that will be very negligible as compared to this Stark effect because of this strong electric field which is applied. So we are not considering L and S quantum numbers. We are considering only N quantum number in the case of Stark. Okay, so these are some introduction towards that Stark effect. Now we'll look more in deep to the Stark effect, what is happening inside these energy levels when we apply the electric field, how the energy level splits, all those things, and what exactly this um, shift first order and second order Stark effect. Also weak field Stark effect as well as strong field Stark effect. That all those things we will discuss in the next. So here we have given some important points regarding the Stark effect. Now we are not yet discussed about what is exact mechanism which is happening. We know only that it is happening because of electric field. The energy level is splitting. The external electric field. Because of that, it is splitting. And now we have to consider that Balmer series hydrogen spectra, and we will discuss more about how this spectra is splitting and what are the different possibilities of this output